All right. Hypothesis testing. So this is what we're going to concentrate on next. There we go. Hypothesis testing. Everybody's got ideas about how the world works, about why people do certain things, how you could get them to do different things. Hypothesis testing allows us to actually go out and test those things to understand what we can rely on, what's something that we could trust to do something again and again in a repeatable fashion. Oftentimes people believe things that aren't scientifically valid. What that means is that they're not something you could rely on to work for other people. We most often take anecdotes. Those are the things that have happened in our life, which is fine, and it's an interesting narrative story to tell people, but we might not understand what the causal connection is between things we do and the occurrences of outcomes that we've experienced. Oftentimes people can make up myths about things. We know this to be true from like animals, right? So if you take an animal and you give it an environment where it can't predict the outcomes of what's going to happen to it, you turn it crazy. It actually starts doing things like, having physical symptoms of illness as a direct response to not being able to predict the safety of its environment. Basically, they did this in shocking dogs. So they put dogs in a cage where they did not know how to stop a painful shock from going to the floor of the cage. These animals, not only did they begin to do neurotic things and try and do some sort of stereotype behaviors that would stop them from getting shocked, but they eventually learned helplessness such that when they were out of the cage that they got shocked in and they were signaled again that they were going to get shocked, that they didn't do anything to try and get themselves out of the area where it was unsafe, that they just laid there and took that. We all have ideas about how this world works, and we need to be able to test them and rely upon these findings. How do we rely upon the findings? We rely upon them with statistics. Statistics can give us, through probability, the law of large numbers, and the central limit theorem, this estimation of what's going to happen in our future. We use this all the time, and you guys might not realize how commonplace it's become for people to understand that this is how we now make decisions. You know, if we have a vaccine that's coming out to treat this virus, we're going to have to put it into a position to compete it statistically against non-vaccine. And if we compete it against non-vaccine, and what we see is everybody in the vaccine group, they develop IgM or IBM antibodies for this virus, and they're protected against it. Whereas everybody in the placebo group, when they're tested, they haven't developed any antibodies. Then we'll suggest that this is a reliable vaccine that we can go with. And so we're going to have to look at the likelihood of that being true, and then when we test it, we'll say, is this a rare event to occur, even if there was no difference between the vaccine and the placebo? This is a confusing thing to think about when you're just encountering it, but it could be that people over time just develop antibodies and we don't know why. What we're going to have to do is compete it to basically the same groups of people who have been treated differently on one variable, and that's either the vaccine or the placebo. And then we'll calculate the probability that the occurrence we see at the end would have happened by chance alone. And if what we find is that the chance of the people who all got the vaccine and they all developed antibodies, whereas only a couple of the people who had placebos developed antibodies, the probability of that happening by chance is so small that we can rely on that vaccination being the causal change in why people increased their immune system's response to the virus. This sounds complex, but we're going to work through it time and time again. And I hope that you guys will stick with this, even though it seems pretty hard to think about initially. I hope that you will sit here with me in your lack of understanding or my lack of clarity, and that we can continue to talk about it and it will become more and more clear. A hypothesis, I hate it when people say it's an educated guess. That's not true. I mean, because I could have a hypothesis about aliens and I've not been educated about aliens. There's no evidence of their existence anywhere. I challenge you to find any evidence of their existence. So it's not educated, but I could still have a hypothesis. In fact, many people do. They even use statistics to try and prove that there must be life elsewhere. Huge problems with this. Huge philosophical, astrophysical, statistical, and psychological problems with this. So aliens don't exist. I can say that forthrightly because there's no evidence for them. And there's even no evidence for why they would exist. We don't know what the base level of that denominator would be for a probability equation that we could answer about how many habitable planets there are, or if we're the only one. We have no idea. We don't know how life arose here. There's no consensus. I'm sorry to throw that out there, but you're college students now. You can take this. Science doesn't explain everything. We don't know how we're here. We know that we're here, but we don't know how we're here. There's some good theories on it, but we can't test them. We can't go to some other exoplanet that has a sun and, panspermia plant something on it, like Crick thinks happened here. We can't just take sort of the Mueller-Urey experiment and try and jam some amino acids together and see if life arose. We can't wait for some deity to just get bored with reality and then create another world. We don't know. We can't test it. So we're limited in what we can test. Some of the questions that we have that we want to ask hypothesis testing, we don't have the ability to ask. So be patient with hypothesis testing, but also recognize that it's the hugest boon for humans to understand a complex world and to be able to make efficacious decisions about how to govern themselves and make human thriving occur more frequently. I'm sorry that I ruined your day about aliens, but they don't exist. Statistically. Okay, what are the steps for hypothesis testing? Well, first, what is it? Hypothesis testing is a method by which we can trust outcomes of probabilistic events to tell us the likelihood that they will occur again, or the likelihood that they would have occurred in the way that we've set up this particular experiment. The first one is to restate the question as a research hypothesis and a null hypothesis about the populations. That's going to take some unpacking. So let's start with what is a research hypothesis and how is it related to a question. So I have a question. I have a question about, you guys are feeling anxious, and so I want to know, does watching these soothing videos help you relax and not be so stressed? So I have a hypothesis, a question. Does watching my videos make you lower your stress level? Now, I don't know if that's true or not, but I could have a question. So my research hypothesis, given my experience with having taught for so long and knowing how students react to me, I'm guessing that I'm increasing your stress. So I'm going to guess that it changes and goes up. That's my guess. My research hypothesis is watching these videos actually increases your anxiety. But I could be wrong. That's something that's important to note, is that we're often trying to find where we're wrong. And if I'm wrong, then watching these videos doesn't make you any more stressed than not watching them. That's called the null hypothesis. So the research hypothesis is the one I have, that watching my videos will increase your stress level. But the null hypothesis states there's no difference between stress levels whether the students watch videos or they don't. That's something that I'm going to have to restate. So I'm going to have to restate my research hypothesis and my null hypothesis. So my research hypothesis would be students who watch my videos will have higher anxiety than students who do not watch my videos, right? So that's my research hypothesis. That's my guess. The only other thing that's possible is that they don't have increased, right? That they don't have increased stress or anxiety. That's the null hypothesis, that there's no difference between student stress anxiety based on watching videos of, Professor Frazee do stats lectures. That it doesn't change their stress level. That's called the null hypothesis. Null is N-U-L-L. Basically no, zero. It's abbreviated H-O. I always used to say ho. Turns out I can't say that anymore because, people hate Santa. So HO, or the HO, it's not actually an O, it's a 0. What that means is it's the hypothesis of zero difference between these groups. The two groups, these two populations, would be the students who watch my videos on statistics and the students who don't. When we measure their stress, again, the dependent variable would be a stress measurement. We find that the independent variable, whether they've watched a video of Professor Frazee teaching stats or not, that's the independent variable, isn't predictive of their level of stress. That's the null hypothesis. We calculate the probability in hypothesis testing that the null hypothesis is true. Okay, this is one of those. Remember, we used to do z-scores where you just subtract the mean from the raw score and divide by a standard deviation. This is different. Okay, so stick with me. The idea is that we're going to test the probability that there's no difference because there's only two possibilities. Either there's a difference or there's not. And in this sense, watching the videos makes them more stressed or it does not make them more stressed. Those are the only two possible outcomes. It either makes them more stressed or it does not make them more stressed. This binary choice allows us to calculate probability on the null hypothesis, that there's no difference between watching my videos or not watching my videos on student stress, that there's no causal effect of watching my videos on student stress. The dependent variable is not moved by either of the levels of the independent variable. We test the probability that that's true. So here's the weird thing. My research hypothesis is that my videos increase stress, but I never actually test that possibility. I only test the possibility or the probability of the opposite of that it does not work. This is a strange thing. A lot of students think that, we test to see if a drug works, right? And that's how we know, this new vaccine will work. We don't actually do that. What we do is we test the probability it does not work. And when the probability it does not work is minuscule, we assume that the other is true. So when they do all these testing trials for the vaccination for this virus, they're not going to actually calculate a probability that it works. They're going to calculate a probability it does not work, and hopefully that probability is very small. That way we can reliably trust the outcome and say, oh, if it's a very small probability that this vaccine doesn't work, the other alternative is it does work, and then we can trust it, and then we can take it, and we'll be protected against this virus. So people don't understand that most often when we talk about hypothesis testing and probabilities and research hypotheses, that we're not actually going to test the probability of the thing that we think working. We're going to test the probability of it not actually working, and hopefully that probability is tiny, small, minuscule. If it is, then guess what the alternative is likely to be? That we were correct in our hypothesis. So, step number 1, restate the question as a research hypothesis and a null hypothesis about the populations. Now, which populations? Okay. There's two populations. Students who have taken my class and students who have not, or students who have watched my video and students who don't watch this video. So, the research hypothesis would be students who watch the video will have higher stress than the students who have not watched it. The two populations are students who have watched it and students who have not watched it. That's it. Those are the two populations. So population number 1, say students who have watched Professor Frazee's Psych 330 videos. And population number 2, students who have not watched that. The dependent variable is obviously stress rating, and we can calculate the probability that those two populations, students who have watched it and who have not watched it, are likely to come from the same population. That the samples we got of students who watched my videos and those who didn't, what we calculate the probability of is that they came from the same original population. That means that they're not different. We calculate the probability that they're not from a different place. And that's step 1 of hypothesis testing. There's 5 more, right? There's 6 total steps. You might be curious because the book only says there's 5, but trust me on this one. There are 6 steps to hypothesis testing. All right, we're back to hypothesis testing with step number 1. Step number 1 suggests that we need to restate the question as a research hypothesis and a null hypothesis about the populations. So I have an idea. My idea is that giving kids awards for participation actually decreases their self-esteem. So I have an idea. There's 2 populations. Population number 1, that's the group of students who gets participation awards. People who get participation awards. Population number 2, people who don't. People who earn their awards. So these are the 2 populations that we have. The ones that I'm concerned with are if this, giving people participation awards, is going to decrease their self-esteem. So there's 2 populations, right? These are independent variable levels. So there's the one that people who earned their awards, and then the people who got participation awards. We're going to measure both of them on the same dependent variable. That will be self-esteem scale. I've made up some survey about their self-esteem. My hypothesis is that they're going to be different. I think that this group is going to be lower than this group. So how do I write out my HA? My HA is my hypothesis of the alternative. The alternative to what? Ha! Like you found it. Ha is the hypothesis of the alternative. The alternative to the null hypothesis. So let's start with that, because we always start with the null hypothesis because it's the only thing we actually calculate the probability of. So I know that my null hypothesis is going to be predicated on what this is. So let's start with the null hypothesis, the HO. We'll start with the HO. HO is not HO. It's not HO. It's H subscript 0. Subscript 0 means that there's 0 difference between these 2. That's what we're going to start with in hypothesis testing, is the idea that these 2 groups are not 2 groups, that their self-esteem is the same, and that them being in different groups, whether they earned awards or got participation awards, that's not any sort of causal connection to their self-esteem. So how would we write that about their self-esteem? That population number 1, the ones that get participation awards, that their self-esteem is not different from population number 2. How do we write not different? Equals the self-esteem of population number 2, this population who earned their awards. So that's how we write the HO for that. Now, HA, which is what I'm concerned with, although we'll only calculate the probability of this, HA states there's an alternative to this. This might not be true. In fact, population 1 might have lower self-esteem, less than self-esteem, than population number 2. So now what we have are 2 possibilities, right? We've got the possibility that there's no difference, i.e. their self-esteem is equal, or, this is my hypothesis, that population number 1 actually has lower self-esteem than population number 2, the people who earned their awards. That's my hypothesis. I can't test that hypothesis. I can, however, calculate the probability that these 2 came from the same place, i.e. that they're the same. If this is very low probability that this is true, the only alternative is that my hypothesis was correct. So that's how we're going to get towards this question of, does giving people participation awards change their self-esteem for the worse? Oh, you're still here? That wasn't clear? All right, we'll do more examples. So the second step of hypothesis testing is to determine the characteristics of the comparison distribution. What we mean by that is, remember when we had the 2 populations, the people that got participation awards and those who earned their awards? The comparison distribution for us is going to be, who are we going to compare the people that earned awards to, and that will be comparing them to people that earned participation awards. So what does the population of people's anxiety look like who have participation awards? Let's say that the average person who got participation awards, they had a mean anxiety of 20. Standard deviation for that population was 3. So now we can fill out this population just like this. We know that the comparison population is those people who got participation awards, and we're going to be comparing our group of people who had to earn their awards to this population. So we know this population is normally distributed, that it has a mean of 20, standard deviation of 3, and so 95% of people who got participation awards have anxiety levels between 14 and 26. That information will be given to you when we do z-tests. That's what we're going to be doing as an example here, is a z-test. You'll have this information, the mean and standard deviation of our comparison population. So all you need to do to complete step 2 of hypothesis testing is determine the characteristics of the comparison distribution, is find the mean and standard deviation of the population that we are going to compare our sample to. So we've determined the characteristics, that is the spread or the variability, and the mean, the average number of our comparison population. It's easy to do with the z-test when you're given that population mean. This step becomes harder and harder as we go into new forms of inferential statistics like t-tests. So later it will be more difficult, and there will be some subtle nuances to how we calculate that particular number. But for now, we're just going to compare our person who did not get participation awards and had to earn her rewards. We're going to compare her anxiety to the group of people who got participation awards and where their anxiety is. Here we are at step 3. Step 3 is to determine the sample cutoff score on the comparison distribution at which the null hypothesis should be rejected. So if you have a hard time remembering this, it's to determine the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. It's a little helpful dance moves for you slash charades. So, determine the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. This is a big mouthful. It's the longest step. But really what we're doing here is saying, well, if we find our sample where its score is, where would we say it's probably not part of this population? Where would we say it's probably part of some other population, meaning that there's a difference? If we find our sample score is right here in the middle of our comparison population, we're going to say that our sample is no different from this population. It's the same thing. But if we find our samples way out here, then we're going to say, hey, it's unlikely that our sample is from this population. Or if we found it down here, it's very unlikely that our sample is from this population because there's very few people in this population that have scores like that. Remember how unlikely it would be for me to get 4 aces or for me to flip a coin 4 times and get heads in a row? That's out here. Unlikely. This is the super, super improbable place. We have to find where on this comparison distribution we are going to make our mark and say, you know, if our sample is anywhere beyond that or beyond that, then we're going to say it's probably not from here. And we're going to suggest that perhaps it's not the same as this population. That maybe the stress levels of people who get participation awards are higher than those who earn their awards. Okay, we're still on step 3. What we need to talk about is the idea of how do we determine where on this distribution, our comparison distribution, the group that we're going to compare our person who does not get a participation award, where do we say we're going to cut off? So typically in sciences, they'll use p-values of 0.05 or less. So where that came from, have no idea. but it's become a standard where we say, hey, you know, if I do this type of a equation, I will find, oh, hey, what's up, man? Okay, so I literally have no idea where I ended that last one because my neighbor came over. I'm sitting in my garage, just you know, sitting here, hanging out. And he walked up here, and so I don't know what I told you last, but I do know we're on step 3. So step 3 is to determine the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. So we had to figure out where here is an appropriate place to say, yeah, it's not from this thing. It's unlikely that we randomly sampled something and we got it out of a distribution that looks like this. It's probably from a distribution that looks different, which means our research hypothesis is probably true if there's a low probability that we select somebody from the null hypothesis population. So that's another word that we talk about with this comparison distribution, is the null hypothesis population is basically saying that our comparison distribution is the same one as that our sample comes from. We're going to select one person. She's not going to get any participation awards, and then we're going to test her anxiety versus her peers who all got participation awards for just showing up. We're going to see, does our research hypothesis stand up in that she has lower anxiety than the rest of the population that all got participation awards? That's the question. We also discussed that the idea is that 0.05, or the 5%, the lowest 5%, or the top 5%, or in fact the lowest 2.5% or the top 2.5%, are the outliers. These are the outskirts. They're in the tails of the distribution. And for some reason 5% became a standard to sort of say a p-value less than 0.05 meant that our sample doesn't come from a population that looks like that. So if you hear significance, statistically significant difference, that probably means that the probability that that sample would come from the comparison population is less than a 5% chance. Again, less than a 5% chance is like, I don't know, if I had a coin and I flipped it 6 times in a row and I got heads, 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 heads. If I did that, you should start saying, I think something's going on. I think he's probably not flipping that coin fairly, because we should start to see some tails coming in there just because of the probability. Similarly, about the same concept is that if we see something that's very unlikely to occur in a population, then we can suggest perhaps that that difference is related to the idea that this person did not receive participation awards and that they are less stressed because of that. Now, where is that cutoff here? We're going to have to figure out what's the lowest 5% of anxiety in this distribution. So if you want to look in the book and you want to turn to the back of the book, you can find where it says 5% in tail. Now again, it's not going to have a z-score that's corresponding to the negative side. It'll be a z-score that's right here, 5% in tail here. But whatever z-score number that one is, it's just going to be the same one, but negative. Because again, this is a unimodal and symmetric distribution. In the normal distribution, we only have that one table in the back of the book, because you could just write the other one would be the same table just with negatives in front of it. So when you turn to the back of the book, you're going to find 2 things. Literally, there's going to be 2. One of them is going to be 1.64 as a z-score, and one of them is going to be 1.65. Now the book chooses one. The book actually says we're going to choose 1.64. And in our case, it would be, this number is 1.64. That 5%, it says 5% is in tail of a z-score of 1.64. That's what the book says. But if you look at the actual chart, 1.64 or 1.65 are equidistant from one another in terms of not actually being the bottom 5% or the top 5%. It's 4.95%, bottom 4.95%, or the bottom 5.05%. That's actually the distinction between a z-score of 1.64 and 1.65. The book chooses 1.64. If you choose 1.65, I ain't mad at you. I'm not going to mark you off. I ain't mad at you. Because you're thinking, and you're just saying, that's a negligible difference. Like, there's no right answer that it's 1.64. In fact, 5% isn't even a right answer, that if we find something is less than 5% chance of happening due to chance alone, then we're just going to reject the null hypothesis. This stuff has been made up over time and isn't substantiated by any logical or reasonable thing. It's just been done over time. So the standard is to say, look, there's less than a 5% chance that I'm wrong if I say that something up here isn't from this population, because it only occurs 5% of the time in this population. Similarly, if I say that something here is not from this population because it only occurs 5% of the time in this population, there's only a 5% chance that I'm wrong that it doesn't come from here. Again, this is a little bit of mental gymnastics. You got to think about it. We're trying to determine if getting participation awards, this is our comparison distribution, if that makes people more anxious than when people have to earn their rewards. So we're going to put a sample person, and we're going to find where that sample person who doesn't get participation awards, they have to earn their awards, where they are on this anxiety scale. And we're going to have to figure out where, if they're at a certain place, we're going to say, yep, because they didn't get those participation awards, they have less anxiety. And we'll know that we'll be wrong saying that particular thing less than 5% of the time. So if you choose 1.64 or 1.65 z-score, because percent in tail is 4.95 or 5.05, good on you. Good on you. Go for it. In this sense, because we're looking to see if it lowers anxiety, we're going to have a negative. Come on now. Negative 1.64. Negative 1.64. We'll stick with that because that's what the book says. It says that basically is a z-score representing that less than 5% of z-scores in a distribution have z-scores that are more extreme than a negative 1.64 z-score. Remember this, the average of the group has a z-score. Something's... The mean has a z-score of 0. Our target has a z-score of 1.64, but if you remember, step 3 says to determine the cutoff sample score. And the sample score is a raw score. It's not a z-score. We know the z-score, it's going to be a negative 1.64. We got to determine what is this? What is this thing right here where that score happens in this distribution 5% of the time or less? How do we do that? We employ that same exact formula that we learned before. X, or the raw score we're looking for, is equal to the z-score that we know times the standard deviation that we know plus the mean that we know. Now, in our case, because this is a mu and a sigma, you employ mu, or you employ sigma and mu. That's it. But it's the same process. So we know the average for this group, or the mu, is 20. So we'll put 20 in there. We know that the standard deviation is 3, because 20 and 17 are 3 apart, and 20 and 23 are 3 apart. So the standard deviation is 3. So we put 3 in here. And we know the z-score that we found out that we need to find the lowest score that would be sufficient for this, or the highest score that would be sufficient for this, which would be a z-score of 1.64, the corresponding raw score. So we say the z-score is a negative 1.64. I have no idea why I can't get functioning. Oh wow, this thing exploded. Check that out. You ever seen? I exploded this thing, and I'd never seen the inside of a dry erase. I wonder if it works. Oh, now it works. Great. I shouldn't have broken it. Great. Now it works. Pretty. Okay. We need to now calculate this formula. Negative 1.64 times 3 plus 20, and that's going to give us the score that is our raw score for step 3, right? We have to determine the cutoff sample score on our comparison distribution at which the null hypothesis should be rejected. So, if anybody out there has their calculators open and ready, we're going to do 1.64 negative times 3, which gives us a negative 4.92, plus 20. and that gives us 15.05. I gotta find something to write with, folks. Okay, see if this one works. Otherwise, it's getting chucked right out into the street. I'm gonna have to go clean up later. All right, so our cutoff sample score says it's 15.08. 15.08. This is a good one. This is solid. 15.08. It makes sense because it's between what we already knew were 2 standard deviations below the mean, or a z-score of -2, which was 14, and a z-score of -1, which was 17. It's in between those two. So 15.08 is our cutoff. If our sample score, if the person who we say has to earn her awards and doesn't get in all these participation awards for just showing up, if she has a stress level less than 15.08, we're going to reject the null, and we're going to say that getting participation awards makes people have higher stress. We'll get to that after we do step 4. Okay, step 4. Step 4 is pretty easy in hypothesis testing because, well, especially with a z-score, I'm just going to give it to you. I'm going to tell you what that person's anxiety score was. That was our sample that we said, you don't get any participation awards, you've got to earn your rewards. She had a stress level of 18. Okay, so that was her stress level. So the sample score, X, was 18. So on step 4, all you have to do to determine your sample score on the comparison distribution is literally write down X equals 18. I've given it to you. Now, this step is gonna get harder in the future, but really not that much. What we need to do is to determine your sample score on the comparison distribution. So we have to go back and then put 18, which is our sample score, on that comparison distribution and say, where is it in conjunction with that already defined line in the sand of where we would reject the null hypothesis. So next step is gonna go put 18 on our comparison distribution. So let's head back and do that now. My wife doesn't want to be in these videos, but she's right there. That's her. She doesn't want to be in them. She's like, do your work. Whoa, almost dropped the camera. All right, so here we are. We're back at our comparison distribution. Hopefully you can see that. Oh, it's focusing on me. All right, we're back at our comparison distribution. For step 4, what we need to do is now, so step 4 is to determine your sample score on the comparison distribution. So we've drawn it out. We know where the cutoff is. If anything's below this level, we know what we're going to say. We're going to say that that's not from something like this, therefore it's different, and getting participation awards really makes people's anxieties go up. However, what did we find? We found right here that our sample score had an 18, right? That her X was equal to 18. On to step 5. Step 5 of hypothesis testing is to decide whether to reject the null hypothesis. Now, if our score, our sample score, is further or more rare in the tails of the distribution past where we put that line in the sand saying, if it gets past here, we'll reject the null. If our score is in that, then we reject the null hypothesis. Again, the null hypothesis was that there is no difference between these two particular groups, i.e. the group that got rewards just for showing up, the participation awards, and our person who we didn't give her any awards unless she earned them. The null hypothesis says there's no difference in their anxiety. We could reject that only if her score, when we checked her anxiety score, was below that standard that we marked in step 3. Now in our case, we found that it wasn't sufficient, it wasn't quite there, and so we're gonna fail to reject the null hypothesis. Now this is the first time I'm gonna talk to you about the book being wrong. The book says that our study is inconclusive. Did you hear what I said? Inconclusive. If you're familiar with the English language, you know to conclude something means that you make a decision. It's synonymous with deciding something. And it means that we know something now. We know something that we didn't before. We didn't know something when you decided it, and now we know that thing. To be inconclusive doesn't mean what you think it means in this sense. It just means that we didn't confirm what we thought. In fact, what we thought was incorrect, or it's probable that it's incorrect. We didn't get to reject the null hypothesis, so our idea about giving a participation award would increase anxiety, we can't confirm that. It doesn't mean that we don't have a decision. No, we've confirmed it. We've found we don't think that making people earn their awards will make them more resilient or help them to be less anxious. We can't confirm that. We tried. We did that with one person. We measured her anxiety, and it was not sufficient for us to conclude that there's any difference between people who get participation awards and people who earn their awards based on their anxiety. Now, one of the critiques you might make of this is going to come soon, and that's going to be, why did we only test one person? Maybe she was just somebody who was super anxious and it actually did really reduce her anxiety to do that. Shouldn't we test multiple people with this? And yes, that's actually coming up next chapter, called Testing with Means of Samples. But I'm just going through the process now of how to complete the 6 steps of hypothesis testing. You might think we're done here because hopefully you're reading the book and you're like, Professor, there's only 5 steps. No, there's one more step, and we're gonna have to use it. It's the most important step, even though I made it up. Here with Caleb, this is my oldest. Now, the 5th step of hypothesis testing was decide whether to reject the null hypothesis. And you might think that the book stops at 5, but our class doesn't. We go to the 6th. That's why he's here. Because the 6th step is Dr. Frazie's step, the 6th step of hypothesis testing, and it's the most important because if you do all those other 5 steps without making an interpretation, right, that finishing move,
Finish him,
that we talked about, organization, analysis, and interpretation is what statistics is all about. So the 5 steps that Aaron and Coops puts forth is not sufficient. The last step, Dr. Frazie's 6th step of hypothesis testing, is explain it to a 7th grader. I do that in honor of him because he's a 7th grader now. Usually I say to that, for all the years before I've said explain it to an 8th grader because that's what the New York Times is written at an 8th grade level. But he's super smart. He's like an 8th grader. So explain it to a 7th grader who's like an 8th grader. All right, so 6th step of hypothesis testing, explain it to an 8th grader. Thanks, Caleb.
Okay.